Good morning, dear students. Welcome to this session on Kani's method, Unit 5 of your syllabus. The last session, we have discussed about the uh, the things required for calculating end moments using Kani's method. So those are rotation contributions in particular, because the equation consists of end moment is equal to MAP is equal to MFAB, that is fixed end moment at A, plus 2 times M dash AB plus M dash BA. So this is what is the equation for finding end moment. So we have learned already how to calculate fixed end moments in previous semester in case of structural analysis 1. So now it is to calculate, to see that how you calculate these rotation contribution values. So last session we have taken up this one and derived an equation for rotation contribution, and also the involved parameter is rotation factor. So rotation factor is like minus 1 by 2 k times sigma k, nothing but k of that particular member, stiffness of that particular member, divided by total moment at that joint. Okay, so this is what is derived in the last session. Rotation contribution uh, of NDA in a member AB is equal to rotation factor multiplied by sum of all fixed end moments of that particular end, and also far end rotation contributions from all far ends. Okay, so this is what we have done in the last session. Right, today in this session we will talk about step by step procedure how you solve for final end moments in a structure using Kani's method. Okay, so the step one is you assume all the nodes as fixed. Calculate fixed end moments. So step one is to calculate fixed end moments. It is very similar to the moment distribution method. So step one is to calculate fixed end moments. So take each member, fix the member at both ends, apply the given loads, write fixed end moments, which are already learned. Okay, right. Next, what in case of moment distribution method, we used to calculate distribution factor. Now we calculate rotation factor for the members at a joint. So again, you can make the similar tabular form for this, like joint, member, the different columns, member, okay, and k value of that member, and then sigma k of the joint, and then instead of distribution factor, now you have to calculate rotation factor. So these are different columns, 1 2 3 4 5 columns you have to make, and number of rows will depend on the number of joints you have. And rotation factor formula is like minus 1 by 2 times k divided by sigma k. It was simply k by sigma k distribution factor, whereas rotation factor formula is like minus 1 by 2 k by sigma. So that is step 2 to the rotation factors. So rotation factor formula is like minus 1 by 2 k by sigma. So that is step 2 to calculate rotation factors. Now As a step three, we used to go for distribution process in case of moment distribution method, like taking a joint and calculating total moment at the joint. To make it zero, you are going to add the opposite value according to the distribution factor. Now here, what you need to do, calculate near end rotation contribution of a particular member at a joint by assuming far end contribution as zero wherever it is not available. So you have to take all the ends, like say if you have so many ends like A, B, C, D, so like A, it's like B, C, D. So calculate rotation contribution of A, rotation contribution of B in AB, rotation contribution of B in BC, likewise C in BC, C in CD, and D also. So likewise, you calculate m dash values of all these, like m dash AB, BA, BC, CB, CD, DC. So likewise, you calculate all rotation contributions. Okay, but all rotation contributions might not be required in some cases. Like for example, if A is fixed, you don't have rotation contribution, right? It won't rotate, so zero. So only in such cases you have to calculate rotation contributions of joint, the members at the joint. Okay, so that is what is written here. Calculate rotation contributions of members at a joint. Okay. Now repeat the calculation of rotation contribution till the difference of two successive values are same. I mean difference is negligible, or else the two successive values are same. So if contribution value is say some 10.21, and very next cycle if you get 10.20, so what is the difference? 0.01. So you can stop the cycling process. So those are final rotation contributions. Now apply the formula to calculate final end moments by using this formula. So fixed end moment plus 2 times the rotation contribution of that particular end, and a far end contribution. That means for A, B is the far end. For B, A is the far end. So likewise, you have to get final end moments. Okay. So this is the procedure to solve any structure using kani's method. So it's very similar to moment distribution method, but little bit a change in calculations, right? So first step is very similar, same thing, fixed end moments. Second step, there is a change. Instead of distribution factor, you get rotation factor. Okay, very similar table. The third step, there we will balance and carry over and go for number of cycles. Whereas here we calculate rotation contributions every time. Cycle 1 rotation contributions, then cycle 2, cycle 3, cycle 4, till the two successive values, two immediate values are almost same. That you decide how much should be the difference between those two consecutive values. Okay, so almost 0.01 is acceptable. Okay, so this is how we proceed for the kani's method. Next session we will discuss an example how to solve, right? So This is a procedure for solving Kani's method. We'll follow these discussed steps to solve an example in the next class. Okay, thank you.